Today I'm going to talk to you about Jinq, which is a system for doing LINQ-style queries in Java 8. So as we all know, databases are amazing. So they do all sorts of really hard things related to persisting data to disk for us, like transactions, consistency, fault tolerance, et cetera, But as language designers, databases are interesting too because in a way, since most databases are accessed through database query languages, these query languages are essentially domain-specific languages, and they're very powerful and they're very widespread. So for example, here we have a typical sort of database query. So here we go, and from a database, we get all the products from the database. Then we restrict which products we want. So we only want those where the price is less than $100. And we say we only want the name field from those databases. Now, because databases are so widespread, there's various, of course, there's many different ways of embedding these database query languages inside Java. So here's a sort of typical way that a database query language might be embedded in Java. So you'll have an interface, and you'll have a method here. And when you call that method, you want it to actually execute that query. So what happens is in the interface, you would annotate the method with this annotation. And you'd stick a string with the actual query string that you want to execute on the database inside the annotation. And what happens is when you run your program, your database framework will find this interface, see the annotation, and it will automatically create an implementation for that method that would execute that query on the database. And these sorts of techniques work fine, but they always have problems with corner cases. So there's always some weird corner case that can't be expressed well or where things get a little clunky. And people are always looking for better ways of embedding these domain-specific languages into Java. So LINQ is a system from Microsoft for doing database queries in C#. And people generally like this system. So the corner cases, the way it handles them are much less bad. It's more elegant. And it handles like more corner cases better than the other systems. And basically, with LINQ-style queries, you express your queries using Lambda functions. So here we have sort of a typical database query. And here is how it would be expressed in C#. So you can see here this where clause would just become a where method. This expression here just becomes a Lambda expression here. And similar here, where here we have a select clause with an expression, that just becomes a select method taking a Lambda expression. Now, the problem with LINQ-style queries is, well, LINQ stands for Language Integrated Queries. So what Microsoft did is they added a bunch of extra facilities into the C# language, specifically for handling sort of these LINQ-style queries. Now, Jinq is a system for doing LINQ-style queries in Java, but unlike LINQ, it doesn't require any compiler or VM changes or other tool chain changes. So basically, it's just a library. You include the library in your code. And afterwards, when you write your regular LINQ-style queries, it'll be translated into SQL that can run on a database. No weird things you have to change it with your tool chain or anything like that. So why should you care about Jinq? Well, first of all, databases are important. Some systems, sort of like Ruby, one of the main reasons it's popular is because of the Rails framework, which is a database and web framework. And of course, many people choose C# just because they like LINQ so much. And another reason is that Jinq sort of is a good example of how far you can push sort of this metaprogramming stuff on regular Java. Like, it's a practical and useful system that successfully embeds domain-specific language into Java. OK, so I'm going to sort of cover 3 topics. The first thing I'm going to cover is sort of the syntax and semantics of LINQ, just to make sure you sort of understand what Jinq is trying to translate into a database query. I'll then cover the translation issues, so how Jinq is able to translate this Java code into a database query. And then finally, I'll just cover some complications I encountered when developing Jinq. OK, so as I showed before, these LINQ-style queries, they're just written as Lambda operations over collections. So basically, it's exactly like working with large lists of data in any functional programming language. So basically, here we use where and select because it matches the database terminology. But this could just as easily be written as filter and map instead. So basically, you're just like in in Scheme or Lisp, where you'd filter or map operations in a functional language, you can do the exact same thing with sort of these LINQ-style queries. And because of that, these queries use sort of familiar semantics that programmers are familiar with. One advantage, though, is since all this code is written in Java code, you automatically get Java type checking and Java syntax checking. Because this is Java code, the Java compiler will automatically do your type checking for you. And so then the error checking you have to do on your side is just much less. So conceptually, as I said, when you sort of building up the queries using these LINQ-style queries, it's exactly the same as just working with large lists of data in a functional language. So when you call db.products, this method is just the same as getting all the products from the database and just putting it in a collection in memory. When you call the where method on the collection with this Lambda function, basically you just apply the Lambda function to all of the products and you filter things. So the CPU where the price is greater than 100 gets filtered out, and that just gets put in a new collection. Then when you call the select method, again, this is just exactly the same as a map operation on a functional list. So you just apply this Lambda to all of the products, and you get the names of all the products. Now, conceptually, this is what happens, but obviously this isn't what actually happens, because reading all the products from the database into a collection in memory, that's going to be really inefficient. And doing all the filtering in memory, that's obviously bad too. So what actually happens is these collections are backed by database queries, and these database queries are evaluated lazily. So when you call db.products, what happens is you create a collection that's backed by this database query. So basically, it gets all the products from the database. When you call this where method on this collection, what it does is it sees the query that's backing the collection, and it just modifies the collection. So it analyzes this Lambda function, and it just sort of slams it into the database query here. So here, instead of just getting all the products, this collection will get all the products with this restriction. And then when you do this map operation with select, basically inside the select method, it will analyze this Lambda function. It'll see you want the name field. So instead of actually doing the filtering in memory, it'll just change the underlying database query underneath the collection. So then when you actually try to get the data get some of the data from the collection, what will happen is that it will then go to the database, run this query on the database, and the database will actually return the data directly. So you can see here the key to getting LINQ to work is somehow inside this where and select method, you have to analyze these Lambda functions and figure out how to slam these things into the query. And that's what I'm going to talk about next. So that's the key. That's the key to the translation. So what does Jinq do? So as I said again, Jinq doesn't do any changes to the compiler or the VM or anything. So what it does is it just uses a lot of bytecode analysis. And this actually works OK because the bytecode format's fairly static. So even hopefully as the language changes, because the bytecode format is static, we won't have to change the Jinq system a lot. But it is it's a little bit tricky because different compilers produce slightly different output for the same piece of code. You can't do simple pattern matching. And basically, the trick we use is just we use some basic symbolic execution, so a simple form of symbolic execution. So I'll go through an example a couple of times to sort of show how the translation works with the symbolic execution. So let's say we have this query here written in Java. So you go get all the products, and you sort of restrict it to the products where the price is less than 100. So again, what you want to do is inside the where method, we get this Lambda function, and we have to figure out what is this Lambda function trying to do. Now, this Lambda function, what we do is the Lambda function, we go and get the bytecode for it. And once we get the bytecode, we have to sort of figure out what the bytecode is doing. And I'm not using real bytecode here, obviously. This is just some sort of low-level pseudocode. But different compilers might compile it in different ways. And we have to figure out what this compiled code does. So let's just look at this first example here with this first bit of compiled code. So let's say inside the where method, we get this bytecode, and we want to figure out what it does. Now, normally, just as a person, if you get a bunch of compiled code and you're trying to figure out what it does, you just create some fake input, run it through the code, and you sort of see what happens, and you try to develop some intuition about what the code does, right? So you might track all the side effects, so all the things that change in the state of the program from running that code with this sort of fake input. So basically, if you run it here, the parameter, this argument p becomes this CPU. The first line, a equals 100, so you'll set that as something that changes in the program. A is set to 100. When you run the second line, b equals p.getPrice, the price of p is 110, so you stick that in b. P becomes b less than a, so b is actually greater than a, so p becomes false. And then you return p. So since p is false, you return false. So basically, if you see here, when you run this function with this sort of fake input, these are all the things that change. And if you run this function with a bunch of different input, you'll see, OK, you'll get some intuition. And you'll see, OK, what the function does is it checks whether the price is less than 100 or not. Now, obviously, you can't get a computer to run this as an algorithm. So what we do is we run the function symbolically. So we just use symbols as input, and we run it through the code. So this lets us see what the function does for all possible inputs. So here we take p, and we set it to a symbol, like the input. When we run the first instruction here, a equals 100, we set this as a side effect as well. Here we have b equals p.getPrice, and p is this input symbol. So basically, b becomes input.getPrice. We set p to be b less than a. So b is input.getPrice, so we stick that here. Less than a is 100, so we just get the less than 100 here. And then finally, we have return p. So basically, everything, this expression here that p is, that's what we return. So basically, these are all the things that the function changes when you run it. And these first 3 lines are changes to local variables. And basically, when the function exits, we don't, these changes are discarded, so we can ignore that. So basically, we're left with this one change here. So from this, we can see by running this function, all it does is it returns whether the price of the input is less than 100. So when we actually run the code, we can do that we can sort of generate queries from it. So again, when you run db.products, as I mentioned before, it's backed by this query here, which gets all the products. And then when you call the where method, we get this lambda function. And inside the where method, we analyze the lambda function. And we can see that what it does is it checks whether the price of the input is less than 100. And from this expression, we can then slam it into the query to create the new query. So this works fine for sort of this example here. But things can get a little more complicated. For example, actually, in a real Java compiler, the code it compiles looks more like this code here on the bottom, which has some branches in it, which sort of makes things a little bit more complicated. So I'll show how we're able to handle the branches there. So with this second route, it has some branches in it. So all we do is we build a control flow graph of this code. And then for this code, we look at all the paths through this control flow graph. So in this case, there's 2 paths through the code. We can take this left path here, where this if instruction returns true. And we can have this other path here, where this if instruction returns false. So there's, depending on which way the branch goes, we have 2 different paths. So then we can analyze each path separately. And then we can use the same. And once we have a path, it's basically just a straight line set of instructions. So we can use that symbolic execution that we did before. So it's a little bit different, though, in that not only do we want to track the side effects, we also want to track the preconditions. So the preconditions are the conditions that have to hold in order for this path to be executed. So just to go through it again, so we set p to be a symbolic input. When we run the first instruction, we see that a is set to 100. The second instruction, we have b equals p.getPrice. So p is input, so b becomes input.getPrice. And then we have this branching instruction. And in this case, for this path, the branch should be evaluate to false. So what we do is we take this branch, nothing changes, but we set it as a precondition. So since in this path we know that we want this branch to be true, we know that whatever is inside this if instruction has to be true as well. So this b less than a becomes input.getPrice less than 100. That's a precondition for the path. And then finally, we get the return 1. So we get the return 1 as a side effect. So these are all the things that happen when we execute the path. Again, as before, the first these changes to local variables, we can ignore them because these local variables are discarded when we exit the function. So basically, from this symbolic execution, we see that the path is executed when the price of the input is less than 100, and when it is executed, it returns true. So if we go back to our control flow graph, again, we had 2 paths through the code. And when we analyzed the first path, we found these were the conditions under which it ran. And if we do a similar analysis of the second path, we see that what it finds is when the price is greater or equal to 100, it returns false. So inside, just going back, we had our query. And inside the where method, we get this lambda function. And we had this analysis for the 2 paths through the lambda function. So basically, inside the where method, we're interested in when the lambda function returns true. So basically, we can sort of figure that out from the analysis of the 2 paths. And what we get is, so basically, we take each path and we just OR them together. The first path returns true when true is true, and when this condition holds, when the price is less than 100. Or we can take the second path. And the second path, it returns true when the thing it returns is true, so when false is true, and when these path preconditions hold as well. Of course, there's a lot of redundant things here. So this is obviously false, and true equals true is obviously true. So we can just cross that out. And then you can see here that we get sort of the same expression we had before. So analyzing the lambda method, we can see that what the lambda function did is it just checks whether the price is less than 100. So as you can see here, this lambda function is compiled in different ways by different compilers. But regardless, we can still analyze it and get out sort of the same expression for what it did. So that's basically it. There's obviously some additional details for handling all these different cases that can show up in database queries. The main complication, though, I guess, is that Java 8 lambdas are opaque. So inside the where method, as I mentioned before, you get these lambda functions. You have to get the bytecode for them and figure out what they do. But reflection doesn't work on these lambda functions, so you don't know what they are. So what happens, though, is lambdas are serializable. So it's sort of ugly. So basically, since the serialization is documented and fixed, you just serialize it, and then you take a look at what, and everything in the serialized format has all the information we need. Of course, writing your own deserialization code is sort of annoying. So basically, what I do is after we serialize the lambdas, the name of the class is sort of written into the serialization format. So you can just change the name here to sort of your own class. So then when you deserialize it, instead of deserializing into a lambda, it deserializes into your own object. And you can sort of extract out the parameters you need from there. Of course, because of the serialization stuff, it has some annoying limitations. First of all, your methods have to accept serializable lambdas. And most of the existing APIs, they just accept regular lambdas. And this is a problem because, like I mentioned before, the Jinq API is very similar to the existing list APIs or the streams API. So it'd be cool if we could just, programmers could just use the streams API and have it automatically generate database queries. But we can't do that because the existing streams API doesn't use serializable lambdas. So if we were to reuse that API, we wouldn't get serializable lambdas, so we can't reuse that API. So we have to create our own interfaces and APIs for that. The other problem is because we serialize the lambdas, all the closure variables, external variables, et cetera, they also have to be serializable. So this sort of restricts the flexibility of sort of what we can be expressed. And the more annoying part is that users find it confusing because they might accidentally use a variable that's not serializable. They give it into Jinq. Jinq tries to serialize it. And basically, all we can report back to the user is not serializable. We can't give them any extra information because in order to give them more detailed error information, we have to serialize it to know what the method is trying to do. And then finally, there's some overhead of serializing and deserializing lambdas. And For databases, this isn't so bad because just executing a database query, you have to serialize the query onto the network. The database has to deserialize the query. It has to actually run some disk accesses to read the data. It has to serialize result sets. And then on your computer, you have to deserialize the result sets. So for database access, the overhead of serializing and deserializing the lambdas is not so bad. But if you wanted to use the same techniques for other systems, like if you wanted to try doing some GPU computation or something, it might not work. So yeah, that's it. So LINQ-style queries in Java, it works. Jinq is sort of like an open source library. No compiler or VM changes are needed. You just include the library and you can go. And so what's interesting about Jinq is it works. And because it works, using these techniques, it might be possible to use these techniques for other systems as well. So that's it.